we'll try to understand the basic concepts in Fresnel diffraction. We'll begin with the Huygens Fresnel principle. For that, let us consider a source S. Here, Mn is a small aperture and xy is a screen that is placed in the path of light. AB on the screen represents the illuminated portion of the screen. Above A and below B is the region which is known as the geometrical shadow. Let us consider Mn as the primary wavefront. Then, according to Huygens construction, the points in the primary wavefront form secondary waves whose envelope form a secondary wavefront. So what you see here as M1, N1 is the secondary wavefront that is emanating from Mn. These secondary wavefronts result in encroachment of light in the geometrical shadow. And this phenomenon is known as diffraction. That is, according to the Huygens Fresnel principle, each point on a wavefront is a source of secondary disturbance, and the secondary wavelets emanating from different points mutually interfere. In order to appreciate the implications of Huygens Fresnel principle, let us consider the incidence of a plane wave on a circular hole of radius A. So this part of the setup form an aperture, and this part will form the screen. The aperture with radius A casts a bright spot onto the screen. The region where there is no brightness is known as the geometrical shadow. The beam, when it encounters the aperture, undergoes a diffraction divergence, and the angular spreading is given by delta theta equal to lambda over 2a. Let us consider the case where a very much greater than lambda. In this case, the intensity at a point r in the geometrical shadow will be negligible. When a very much greater than lambda, the secondary wavelets emanating from different points on the circular aperture beautifully interfere to produce almost zero intensity in the geometrical shadow and large intensity in the inside of the circular region. What happens when A approximately equal to lambda? In this case, there will be almost uniform spreading out of the beam and almost uniform illumination will be seen on the screen. This is because when A becomes equal to lambda, the aperture almost acts as a point source that will result in a uniform illumination of the screen. The diffraction phenomenon can be Fresnel or Fraunhofer type. In the Fresnel class of diffraction, the source of light and the screen are at a finite distance from the diffracting aperture. Whereas in the case of Fraunhofer class of diffraction, the source of light and the screen are at a finite distance from the diffracting aperture. We'll start our understanding on Fresnel diffraction with the concept of Fresnel half-period zones. In this figure, W prime is a plane wavefront propagating in the z direction, and P is an arbitrary point at a distance d from the center of the wavefront. That is, the distance PO is equal to d. We have to find the resultant intensity at P due to the wavefront W dash. For that, we will construct imaginary spheres centered at P whose radii are d plus lambda by 2, d plus 2 lambda by 2, d plus 3 lambda by 2, etc. This is one such kind of a sphere that actually intersect the wavefront. And these spheres will intersect W dash in circles as you see in this figure. So this is one such circle. This is the second one. And again another one. The concentric circular zones in the primary wavefront W dash are called half period zones. And when we construct such half period zones, each zone will differ from its neighbors by a phase difference of pi or a path difference of lambda by 2. So these are the half period zones that are created on the wavefront W dash. Here Qn and Qn-1 are two consecutive points on two neighboring half period zones. Thus, a Fresnel half period zone is a thin annular zone of the primary wavefront in which the secondary waves from any two corresponding points of neighboring zones differ in path by lambda by 2 or in phase by pi. We'll now try to derive an expression for the radius of the nth circle on the Fresnel half period zone. Consider this yellow right-angled triangle. From this right-angled triangle, we can write Rn square plus d square as equal to d plus n lambda over 2 the whole square. From this, we have Rn square as equal to d plus n lambda over 2 the whole square minus d square, or Rn equal to d plus n lambda over 2 the whole square minus d square to the power of 1 by 2. This is dn lambda plus n square lambda square divided by 4 multiplied by d square over d square to the power of 1 by 2. And again n pi d, then 1 plus n lambda divided by 4 d square d to the power of 1 by 2. And this is square root of n pi d times 1 plus n lambda over 4d to the power of 1 by 2. And this can be approximated to be square root of n pi times d. In a half period zone, this distance is radius of the first zone, and this is radius of the second zone. This is radius of the third zone, and let's take this as the radius of the nth zone. We'll now try to find out the area of the nth half period zone. Area of the nth half period zone AN is equal to pi Rn square minus pi Rn minus 1 square. and this is pi n lambda d minus n minus 1 lambda d. And this is equal to pi lambda d. Thus, we see that the areas of all the half-period zones are approximately equal. We are now in a position to find out the resultant amplitude at P by the wavefront. So what you see here in this picture is the wavefront W W dash. We have constructed the half-period zones on the wavefront W W dash, and we are to find out the effect of all these half-period zones at point P. For infinitesimal area surrounding a point Qn in the nth half-period zone, there is a corresponding infinitesimal area surrounding the point Qn-1 in the n-1th half-period zone, such that the path difference Qnp minus Qn minus 1p equal to lambda over 2. This path difference will correspond to a phase difference of pi. Now, the resultant amplitude at P can be written as UP equal to U1 minus U2 plus U3 minus U4 plus U5 plus the terms in between, and the last term will be minus 1 to the power of m minus 1, then um. Let us call this as equation number 1. Here un is the net amplitude produced by the secondary wavelets emanating from the nth zone. And in this expression, we have taken negative signs for the alternate terms. The alternate negative and positive signs represent the fact that the resultant disturbances produced by two consecutive zones are out of phase by pi with respect to each other. Now, the amplitude produced by a particular zone, un, is directly proportional to the area of the nth zone. It is inversely proportional to the distance of the zone from the point P. And it is also proportional to 1 plus cos chi over 2, where chi is the angle that the normal to the zone makes with the line QP, and this is known as the obliquity factor. Thus, we can write un as equal to a constant times an over qnp times 1 plus cos chi divided by 2. As we consider the zones outwards from O, the obliquity factor increases, and hence the quantities u1, u2, u3, etc. are of continuously decreasing order. Thus, u1 is slightly greater than u2, and u2 is slightly greater than u3, and so on. As the amplitudes are of gradually decreasing magnitude, the amplitude of vibration at P due to any zone can be approximately taken as the mean of the amplitudes due to the zones preceding and succeeding it. For example, U2 can be written as equal to U1 plus U3 over 2. Now, the series in equation 1 can be approximately summed by a method by Schuster. That is UP equal to U1 minus U2 plus U3 minus U4 plus the terms in between, and then the final term minus 1 to the power of m minus 1 um. And this can be rewritten as u1 over 2 plus u1 over 2 minus u2 minus u3 over 2 plus u3 over 2 minus u4 plus u5 over 2 plus u5 over 2 plus etc. Let us call this equation as equation number 2. We'll couple the terms like this. But we have u2 as equal to u1 plus u3 over 2 and u4 as equal to u3 plus u5 over 2, etc. And this gives us up as equal to u1 over 2 plus over 2 if m is odd, and u1 over 2 plus m minus 1 over 2 minus if m is even. Now, if the whole wavefront w dash is unobstructed, that is, there are no aperture in between the wavefront and the screen, the number of half-period zones that can be constructed with reference to the point P is infinite. That is, m becomes infinite. And as the amplitudes are of gradually diminishing order, um and um minus 1 tend to be 0. Therefore, the resultant amplitude at P due to the whole wavefront will be up equal to u1 over 2. The intensity at a point is proportional to the square of the amplitude, and I proportional to u1 square divided by 4. And this is an important result. We see that the intensity at P is only 1/4 of that due to the first half-period zone alone. Here only half the area of the first half-period zone is effective in producing the illumination at point P. Thus, if we place a small obstacle of the size of half the area of the first half-period zone, then we can see the diffraction effect of the whole wavefront on the screen. The intensity at P due to the rest of the wavefront will be 0. If the size of the obstacle used is far greater than the area of the first half-period zone, the bending effect of light round corners, that is diffraction effects, may not be observed. And this is true in the case of sound waves also. In the case of sound waves, the wavelengths are far greater than the wavelength of light, and hence the area of the first half-period zone for a plane wavefront of sound is very large. If the effect of sound at a point beyond an obstacle is to be shadowed, an obstacle of very large size has to be used to get no sound effect. We have understood the concept of Fresnel half-period zone. Now, with the help of Fresnel half-period zone, we'll try to understand the diffraction produced by a circular aperture. Consider the first figure. The setup consists of a circular aperture having radius a. A plane wavefront is incident onto this aperture, and its effect on the aperture can be seen on a screen which is placed at a distance d from the aperture. The technique by which we construct Fresnel half-period zones on the planar Fresnel half-period zones created on the planar wavefront can be used to explain the diffraction that is produced by this circular aperture. The method by which we create Fresnel half-period zones have already been discussed. The technique is schematically shown in the second figure. Here, OW represents the upper half of the plane wavefront. To create the Fresnel half-period zone, we'll create imaginary spheres with radii d plus lambda by 2, d plus 2 lambda by 2, and d plus 3 lambda by 2, etc. The intersection of these imaginary spheres on the wavefront will be as concentric circular disks. And this is known as the Fresnel half-period zone. In this analysis, we assume that A can be increased from 0 onwards. As the aperture size increases, the intensity at the point P would also increase till the circular aperture contains the first half-period zone. And for this to happen, the radius of the circular aperture has to be equal to square root of lambda times d. Now, the resultant amplitude at P is twice the amplitude of unobstructed wavefront. In the case of the unobstructed wavefront that we have discussed earlier, we have found that this is u1 over 2. Therefore, the resultant amplitude at P when we place a circular aperture between the planar wavefront and the screen is u1. The corresponding intensity at P would be the square of twice the amplitude for unobstructed wavefront. So this is 4 times I0, where I0 is u1 over 2 the whole square. Now, if we further increase A, then UP would start decreasing. When the circular aperture contains the first two half-period zones, or when A equal to square root of 2 lambda d, the resultant amplitude u1 minus u2 would almost be 0. Thus, by increasing the hole diameter, the intensity at the point P decreases almost to 0. And this interesting result is once again due to the validity of the Huygens Fresnel principle, and hence would be valid for sound waves also. Let's now generalize this result. If A equal to square root of 2n plus 1 lambda d, where n equal to 0, 1, 2, etc., the aperture will contain an odd number of half-period zones and the intensity will be maximum. Whereas, if A equal to square root of n lambda d, where n equal to 0, 1, 2, etc., the aperture will contain an even number of half-period zones and the intensity will be minimum. The zone plate. A zone plate is a specially constructed screen such that light is obstructed from every alternate zone. It can be designed so as to cut off light due to the even numbered zones or that due to the odd numbered zones. To construct a zone plate, concentric circles are drawn on a white paper such that the radii are proportional to the square roots of the natural numbers. The radii of the zones are defined as r1 equal to square root of d lambda. Let us call that as k. R2 will be square root of 2 times d lambda, and this is equal to root 2 times k. Similarly, R3 equal to square root of 3 d lambda, and this is equal to root 3 times k. And Rn would be square root of n d lambda, and this is equal to square root n times k. So from the center, this is zone 1 having radius r1, and this is zone 2 having radius r2, and this is zone 3 having radius r3, and this is zone n having radius rn. In the next step, we will shade alternate concentric circles. So these are the various zones on the zone plate. This is zone 1, 2, 3, 4, 5 and 6. If the even numbered zones, that is zones 2, 4 and 6 etc. are shaded dark, then this type of zone plate is known as a positive zone plate. Whereas if we shade the odd numbered zones, that is zones 1, 3, 5 etc., then this kind of a zone plate is known as a negative zone plate. In this figure, we have placed a positive zone plate between a plane wavefront and a screen. If such a plate is held perpendicular to an incident beam of light and a screen is moved on the other side to get the image, it will be observed that maximum brightness is possible at some portion of the screen at d centimeter from the zone plate. So what we would do is that we will change the position of the screen and place it at P1, P2, P3, P4, P5 etc. and try to find out the intensity that is produced at that particular positions. The radius of the nth zone plate is square root of n times d lambda. Let us call this as k. From here, the distance of the screen from the positive zone plate is d, that is k square over n times lambda. Let us assume that we have placed the screen at position 1. The resultant amplitude at position 1 will be u1 plus minus u2 plus u3 plus minus u4 plus u5 plus minus u6 etc. For the point P1, which is at a distance k square over lambda from the zone plate, the blackened rings correspond to u2, u4, u6, u8, u10, u12 etc. Thus, the even zones are obstructed and the resultant amplitude at P1 would be u1 plus u3 plus u5 plus u7 plus u9 etc. That is, we have only the odd terms producing an intense maximum at point P1. Let us now consider point P3. For the point P3, which is at a distance k square by 3 lambda, the blackened rings correspond to minus u4, u5, minus u6, and the second blackened rings correspond to intensities minus u10, u11, and minus u12. That is, we are left with terms u1, minus u2, and u3, and then u7, minus u8, and u9, etc. The terms in the blackened rings are 0, therefore the resultant amplitude is u1 minus u2 plus u3 plus u7 minus u8 plus u9 plus the other terms. So this would again correspond to a maximum, but it would not be as intense as the point P1. Between the points P1 and P3, there is a point P2 at a distance k square divided by 2 lambda. Let us now try to find out the resultant amplitude produced by the zone plate. When we place the screen at P2, the first zone or the first radius will consist of u1 and minus u2. u3 and minus u4 will be contained in the blackened region. u5 and minus u6 is contained in the second zone. u7 and minus u8 is contained in the blackened zone. Again, u11 and minus u12 is contained in the blackened zone. Therefore, the resultant amplitude will consist only of u1, u2, u5, and u6, etc. Note that the first term is u1 minus u2 and the second term is u5 minus u6. Obviously, the point P2 will correspond to a minimum. Thus, if a plane wave is incident normally on a zone plate, then the corresponding focal points are at distances. Obviously, if a plane wave is incident normally on a zone plate, then the corresponding focal points are at distances k square divided by lambda, k square divided by 3 lambda, k square divided by 5 lambda, etc. The zone plate has a convex lens. The zone plate can also be used for imaging points on the axis. If we have a source S, then a bright image will be formed at point P. So this is distance A, where A is the distance of the source from the zone plate, and this is distance B, and B is the image distance. The point P should be such that SL plus LP minus SP equal to lambda by 2. Let us call this as equation number 1. Also, the point L should be on the periphery of the first circle of the zone plate. Now, if the radius of the first circle is R1, then SL minus LP minus SP, this is equal to square root of a square plus R1 square plus square root of b square plus R1 square minus a plus b. And this is a times 1 plus R1 square divided by a square raised to 1 by 2 plus b times 1 plus R1 square divided by b square power 1 by 2 minus a plus b. And this is approximately equal to a times 1 plus r1 square divided by 2a, where we have performed a binomial expansion. And then this is again 1 plus r1 square divided by 2b square by binomial expansion minus a plus b. And this is equal to r1 square divided by 2a plus r2 square divided by 2b, and this is equal to r1 square by 2 times 1 by a plus 1 by b. Now equation 1 becomes SL minus LP minus SP equal to lambda by 2, that is equal to r1 square divided by 2 times 1 by a plus 1 by b. So this is lambda over r1 square equal to 1 over a plus 1 over b, and this can be written as 1 over f equal to 1 over a plus 1 over b, where f equal to r1 square divided by lambda. If you are considering the nth zone with radius Rn, the equation can be written as Rn square 1 over a plus 1 over b equal to n lambda. That is Rn square times 1 over Fn. This is equal to n times lambda, or this gives us Fn, the focal length, as Rn square over n times lambda. Thus, we conclude that a zone plate is similar to that of a convex or converging lens. A formula connecting the distance of the object and image points can be obtained for a zone plate also. We will conclude the discussion on zone plate with a comparison with convex lens. In the case of a convex lens, the focal length is given by mu minus 1 times 1 over r1 minus 1 over r2. Here mu is the refractive index of the material of the lens, and r1 and r2 are the radii of curvature of the lens. Whereas in the case of a zone plate, the relevant equation is Fn equal to Rn square over n lambda, where Rn is the radius of the nth zone. The second difference is that in the case of a convex lens, the image is formed due to refraction of light. In the case of a zone plate, it is the diffraction phenomenon. The convex lens has only one focus. As all the light is focused at one point, the intensity of the image will be more. In the case of a zone plate, it has multiple foci on either side of the plate. Hence, the intensity of the image formed will be much less. The convex lens forms only real image, whereas the zone plate acts simultaneously as a convex lens and a concave lens. In addition to a real image, a virtual image is also formed simultaneously. The fifth difference is that in the case of a convex lens, all the rays reaching the image point have zero path or phase difference. Whereas in the case of a zone plate, the waves reaching the image point through any two alternate zones differ in path by lambda by 2 and in phase by pi. The focal lengths of both depend on the wavelength, lambda, and hence suffer from chromatic aberration. The chromatic aberration in a zone plate is much more severe than in a convex lens. The seventh difference is that a glass lens cannot be used beyond the visible region, whereas a zone plate can be used over a wide range of wavelengths from microwaves to X-rays.